Okay, hello everyone, good morning. Uh, I put some exercise in the Moodle if you haven't checked. Okay, you can check. This is basically I would say, a typical examples on the matrices. So basically, most of the practices is about computing in matrix, and particularly for the system of linear equations. So that will be um, the main problems. You will find more, I think, more sophisticated and a little bit complicated problems when we are dealing with the differential equations with eigenvalues. So from this eigenvalue that we uh, start to learn, we are going to see that this eigenvalue is also helpful for solving the differential equation. So all the method that we have learned before, like the constant, coefficient, and I think some other, also we have, I think, at least 4 methods. We are going to see a little bit more similar methods with the engineering mathematics one. So that will be the same method. So this is, I think, we have learned how at least to compute, to take the eigenvalues out of this, we call this characteristic equations. And from these eigenvalues, we are going to check each one of them. And there will be 3 eigenvectors from these 3 eigenvalues. So first we check the first eigenvector, and then we could also check the other one with the different eigenvalues. For example, when eigenvalue is 0, we get this eigenvectors, and you can find the same another eigenvectors with different eigenvalues. So you can check and then do row operations and make it the constant 0 and solve the equation and find each solution for k1 or the small k1, small k2, small k3, and you get the eigenvectors 1, 2, 3. And it depends how many eigenvalues you get. That will be your eigenvectors. This is for eigenvalues that are distinct eigenvalues. Now, I think last time we have done this, although I haven't finished last time, but I finished this in this slide here. Yeah, this is the second eigenvector, third eigenvector we have learned. Okay, this one. Okay, so we discussed up until here, and for this case, this eigenvalue. So we still say, although they have the same eigenvalue, 5, which is because this is a square, lambda minus 5 squared, we say that this is going to be a multiplicity 2. So it has multiplicity 2, which means that it has this similar eigenvalue. For 2 by 2 matrix, this is not a problem. We don't really need to check the Gauss elimination, the Gauss method, to check each solution for the eigenvectors. And since we don't need to check, then we can just see from the eigenvalue 5. When we take 5 here, we get this equation, which is very simple. You get the conclusion that is the k1 should be negative 2k2, and we can have conclusions. And usually we are going to set and choose k2 by some number, usually 1 or negative 1 or some constant, that when we multiply the constant, it could be a whole number. Like, for example, if the eigenvalue can be fractions, then we can multiply to make it maybe a better value here. So not really a problem if 2 by 2, if this is 2 by 2 matrix. Now, let me show you if it is the 3 by 3, okay, at least 3 by 3. So let me write here another example. I will make it a little bit small here. Okay, maybe move around here. Resize a little bit smaller. Okay, maybe there. Okay.
and maybe make a line here just to see the example. So if we have another example, let's say we have a matrix A. This is a 9, 1, 1. I think this is a really, special number. So it would be, the diagonal matrix will be 9 minus lambda. So let me write in the determinant form. So determinant A minus lambda identity, this will be equal to, so 9 minus lambda, 1, 1, 1, 1. So that's the determinant set of equations. And by doing the taking the determinant for 3 by 3, we're going to see that it would be I will write the final equations. It should be using the 3 by 3 determinants, and this should be negative lambda minus 11 lambda minus 8 squared. So after some calculation with another addition and subtractions, okay, and this should be equal to 0. So we are going to solve this polynomials, right? Or it's already been solved. I think it's easy to see that we have the lambda, right, black. So lambda 1 is 11, and we see that we have second lambda and the third lambda, which is 8. So we have a multiplicity here. So this is a multiplicity. Multiplicity 2, right? For the lambda 11, no problem. We can use the elimination, Gauss eliminations, using row operations, and we get, I think easily we get, or we can write here for the, okay, for lambda 11, our row operations will be A minus I, or 11I, and equaling to 0. This will be 9 minus 11 is negative 2, 1, 1, 1, 1, negative 2, 1, 1, negative 2. And this should be equaling to 0. And we solve this, making the triangular. And by solving this, we get that this will be 0, 0, 0, 0. Okay. So that this is oversimplification. This is after several row operations. This is what we get. And I think we can conclude that since we have seen that the K2 equal K3 and K1 equal K3, we can set the K3, let K3 equal 1. Then all the terms will be, so in conclusion, the K1 will be 1, 1, 1. Now the interesting part is the second lambda and the third lambda. It will be interesting because we are going to see a very unique row operations. I think I will resize this. I'll prefer all of this in the one page, so that you can see the relations between all of them. Let me resize a little bit, pulling there. Maybe I will put this here, and this is around here, so I can move this up there. Okay. Resize a little bit. Okay, now check the lambda 2 and 3, which is 8. So we are going to take a minus 8i 0 for the row operations. So 9 minus 8 will be 1, and we are going to see 1, 1, 1, all the row. Now we can solve row 2, row 3, and I think all possible row operations, it will make at least two rows will be 0. Okay, you can see that every rows will make another row will be 0, right? Because it is all the same number. So by the row operations, we get this will be still 1, 1, 1, and I will just operate the second row and the third row with each other, which we are going to see that each one of them are getting by 0. Okay? Because it's only 3 rows, so the only possible way to make it 0 are the 2 rows, right? Okay. And because of these 2 rows, and we have some set of equations that all the k1 plus k2 plus k3, and this will be equal to 0, right? Now we can select, so let me write here, so we can freely select select 2 variables. Okay. So for example, the first one we can choose k2 is 1, k3 is 0, and so this is the first case. The second case we choose k2 is 0, k3 is 1, which in turns we get the k1 for the first case is -1, we get the k1 for the second case still in -1, but the k2 and k3 is on different conditions. So the first one we get, let me resize this part first. This is the first one, this is the second one. Now the first one is the, let's say the first one is the k2. This will be -1, 1, 0, and the k3 or let me write k3 bigger, k3, this should be also bigger. This will be -1, 0, 1. And of course,
the result, like for example, if we choose maybe to different order, still okay, still okay. As long as we choose all the like for one another, there will be a pair, right? A pair that is going to be suitable. As long as it is correct from this equation, it should be okay. So that's the difference. So with the 2 by 2, nothing wrong. You don't need to check with the Gauss elimination, and you can just see that it will be on the one possible root. But for this one, since we have these 2 rows that are 0, we can have several roots. We can have this, or perhaps another order that can be set up with another pair. So it can be like no single answers, like no single exact answers, because we can have many choices because of this. As long as this is correct by this equation, so it's okay.
and I think later, if we are going to see some sort of practice just to find the eigenvalue, eigenvectors, you will see that when we are doing the 2 by 2 and 3 by 3, you will see that there are some eigenvectors that will oftenly will occur, and that will be unique. For example, the eigen 2 by 2. Usually we are going to see 1, 1, negative 1, 1, or 1, negative 1. It should be like always occurs, okay, most of the time. Especially for our simple eigenvalue, eigenvectors. And since we are dealing with the polynomial, remember in polynomial we can also have a complex, okay? And that is also a possible outcome. So we have multiplicity, and we can also have a complex when we have the discriminant in, especially in quadratic equation, the discriminant is less than 0, which means that we are going to have a complex, that we are going to include imaginary number. That's also a possible way. And I think in engineering math 1, we are, I think, familiar to include the imaginary number, especially when we solve the differential equations, right? Okay, any questions? Any questions so far? I think most of the problem, if you're dealing only with the eigenvalues and eigenvectors, aside from the row operations, maybe the solving the polynomial. Okay? You should maybe take some notes on some review how to solve polynomial, especially the quadratic equations, and maybe the cubic or the 4th degree. But I think at most the problem will be around 3 by 3, so maybe cubic at the most. So three variables, or 3 values, 3 eigenvalues. Okay, let's move to the next one, which I have introduced the complex eigenvalue. So we have here. So we are going to see that the eigenvalue can be in the complex, the alpha plus imaginary beta or IB. So suppose that that is going to be our complex, and we are going to see the conjugate of that complex, which is the minus part, is also the eigenvalue. So we are going to see that these two values will be our eigenvalues to check our eigenvectors. Okay. So we have the A or lambda for the A alpha plus I beta, and we have the lambda with bar, and we have K, and also we have the K bar, okay, for each one of the eigenvalue, complex eigenvalue. For illustration, let's just see this example. So we have a 2 by 2, which is very simple. Then immediately we can do the determinant for the matrix A minus the lambda identity. Well, maybe to make it some formulation for the eigenvalue, we can write A bar multiplied with the K bar. It gives the lambda bar K bar, or we have A K bar is equal lambda bar K bar. This is just to state that the complex has a conjugate, which is the lambda bar and lambda, and both of this, they are going to make up the matrix A and matrix A bar. Okay, now if we have this eigenvalue for this one, so you can write determinant alpha minus lambda I, and we can write 6 minus lambda, 5, negative 1, 4 minus lambda. Okay. And then immediately we see that this will be 24 minus 4 minus 6 minus 10 plus lambda squared plus 5, or we have lambda squared minus 10 lambda plus 29 equal to 0. And you can directly use the quadratic equation formula, or if you want to complete the square, you can complete the square. So we can write maybe taking plus 25 plus 25. This will be right, and we get lambda minus 5 plus minus, or let me just write directly, since this is already negative, let me write 2 imaginary number. So we have lambda 1 is 5 plus 2 imaginary number, and lambda 2 will be 5 minus 2i. And then for each one of them, we need to check the eigenvectors. And since this is 2 by 2 matrix, I think we can just solve by looking at the system of linear equations, not necessarily doing the row operations. So we can write So for lambda equal 5 plus 2i, we can input into the determinant or into the system of equations. So 6 minus 5 is 1, so 1 plus or 1 minus 2, right? So 1 minus 2i, let's say this is the variable 1 for k1, and minus since this is negative 1, so k2, this will be 0. The second one is 5k1 plus, or here's the 4 minus lambda. So 4 minus 5 plus 2i, right? So we have minus 1 minus 2i, or we can write, since it's minus 1, I will factor out and write 1 plus 2i k2, right? And since we can see from the first line, from here, we can see that the k2 is 1 minus 2i k1. If k1 is 1, then k2 is 1 minus 2i. So the whole eigenvector, the capital K, this will be 1 and 1 minus 2i. And do the same with the conjugates. So we can take the second lambda, 5 minus 2i, so this will be 1 plus 2i k1 minus k2 equals 0. This is 5k1 minus 1 minus 2i k2, right? And again, with the same logic, the k2 here is 1 plus 2i k1. So if k1 is 1, then the capital K for the eigenvectors will 1 plus 2i. Okay, that's the complex. So the important thing here is just the when you have the complex, then you need to check both the complexes, because you will have the plus minus from the square root. Then you are going to solve the eigenvectors by checking both eigenvalues. Okay, I think as long as you know how to compute the finding the roots of the polynomial, supposed to be not too difficult. Okay, now another subtopics before we end the first part of the eigenvalues. So there are a theorem about the zero eigenvalue. So let me write here. So if we have, the standard form for the eigenvalue as this, right? So we multiply the matrix with some vectors k. We are going to get a lambda, multiply with the vector k. And it says that, suppose that if this eigenvalue is 0, okay, then what we have is actually 0 multiplied by k, which is going to be 0. Okay. So if if lambda is 0, then linear system of n equations in n variables, it must have a non-trivial solution vector k. But because of this, then the conclusions, the matrix A need to be singular or if you can see the theorem, it's just I think more clear. So if A is n by n matrix, if the eigenvalue is 0, so it will be the eigenvalue of A if the matrix A is a singular matrix. Or if you want to write in a different way for this singularity, A or matrix A, let me write matrix A is non-singular if and only if the number 0 is not the eigenvalue of A. And since we know that the eigenvalue is by definition related to determinant, right? So let me write here, eigenvalue are related to determinant A. We can write the determinant A minus lambda I. This will be equal 0, and we can say that this is a degree polynomial equation that can contain multiplicities and complex number, and this has n roots which we say the roots will be the lambda 1, lambda 2, lambda 3, lambda n. And by the theory of algebra in the polynomials, then we say that the determinant we can write as lambda 1 minus lambda 2 minus Okay, now if we conclude that it has the roots, and if you set the determinant a minus lambda becomes lambda 1 minus lambda for all the determinants, that is, so basically this is the diagonal matrix. Okay, this is the diagonal matrix that it sets, and if we set, so let me write just to remind you that this is actually the diagonal matrix, right? The diagonal a minus lambda, right? And if we set up the lambda as 0, then we see that the determinant a is actually lambda 1, lambda 2, lambda 3 until lambda n. So the determinant, we say determinant a is the product of its eigenvalues. And in the previous example, it can be seen the complex one. So if a is the 6, 5, negative 1, 4, we know the determinant is going to be 24 plus 5, right? But we can also see that the determinant of a is taking the multiplication of its lambda. So let's say we have two complex, right? Lambda 1, lambda 2, which is 5 plus 2. I think this is pretty much easily to prove because this is basically using the polynomial and finding the roots, and we get exactly that this is going to be 24 plus 4, 25 plus 4, so which is the 29, this is the determinant by multiplying the eigenvalues itself. And we can also consider the determinant to be non-singular because it's not 0. So this is not 0, means non-singular. Okay, the next two are also related to the diagonal. And if you see the next theorem about the inverse, so if you have A and you have the inverse of A,
then the eigenvalue will be representable, or if this is lambda, then the eigenvalue for the inverse is 1 over lambda. Okay.
So this is I think we could see from some a basic identity in matrix, especially if we have we start by taking the A, K, and then lambda K, right? Remember, the eigenvalue will be this scalar, right? So if we multiply with the inverse on the left side, I will multiply on the left side of K, just to make it easy, because they are both vectors, right? Or matrix. So I will write here the A inverse. Okay. Now A inverse A, this will be identity. Let me write I, K, and this will be lambda A inverse K. Okay. Or we can write A inverse K will be 1 over lambda K. So we could see that this is going to be our, supposed to be like the eigenvalue of the A inverse. The A inverse. So this is going to be eigenvalue of A inverse. So if the question may be asking the eigenvalue for the inverse of A, then you don't need to rewrite all the row operations like again. You can just say, okay, this will be 1 over the lambda that we had before. And the last theorem, this is just a conclusion from what we have from this diagonal. So if we have upper triangular, which is a 0 on the top, a lower triangular, 0 triangle on the bottom, and also the diagonal matrix. So they are, the eigenvalues will be the main diagonal. So the diagonal will be the eigenvalues. We can see from what we have here. This is all the lambda, right? So whenever we have upper triangular, lower triangular, and the diagonal matrix, which is only diagonal and the other part are 0, and we can suppose to think that that will be the row operation that has been solved, right? Because all is 0, and either the lower or the upper, if we try to take the determinants, the other part makes 0, right? So it will not affect the other value. So we can just say that the main diagonal will be our eigenvalues. Okay? Okay. Actually, the matrix part is quite long, and I skipped some of them. And maybe I will just emphasize several of them. There are the power of matrix, the orthogonal matrix. That is something that I will skip for now, but we are going to go back for a little bit just to see the relations for that matrix in terms of solving differential equations, okay, which we are going to have. Okay. So for the next part of our class today, I will start taking into the system of differential equations, and we are going to see solving this system using matrix. Okay, we are going to have a break. Okay. We learn the matrices until the eigenvalues and eigenvectors. Then we are going to apply these eigenvalues for solving differential equation. But before we solve, maybe we can take some overview. If we could replace all the differential equation that we learned in Engineering Math 1 in the form of matrix. Okay, so let's rephrase all the definition in the form of matrix, which means we start by taking this as a system of differential equation, and we start by the theory of linear systems. So basically, the theory of linear system, it states that, so if we have this P11, it means that this is going to be the polynomials. P is for polynomials. Let me write here. So P is for polynomials, with various degrees, and the D is the differential operator. So it can be first derivative, it can be second derivative, it can be anything. So it's just to show us it's the operator, differential operator. And what else? And the x will be the variable thing. Okay, I think it's understandable. And we say that we have the first order. This is we call this is the first order, the first ODE, right? If you remember, and we call that this is what we call as a normal form. So if we write in this meaning, that will be the normal form of the first order system. Okay. And we call this as a linear system. And this is a linear system. Linear system in the ODE. So we can write, and we can adjust all the A and adjust all the variables that we call the normal form. This is the normal form. This is the normal form of the first ODE system. And simply, we say that this is just simply linear, a linear system. And remember that linear system, it can be homogeneous or non-homogeneous. The difference is the constant part. If homogeneous, it will be equal to 0. If non-homogeneous, then it will be not equal to 0. And what we are going to replace now is we are going to replace all the variables, the x1, x2, and etc. with parameter t. We are going to replace all of that with the matrix X. Okay. And the coefficient A11, A12, and all of that, we are going to replace with the matrix A. And for the function, or the constant, or let's say the function of t, f1, f2, and until Fn, we are going to have a matrix F. Okay? And then we can write the system as
ddt, all the variables here, as a vectors or matrices 1 by 4, and the coefficient multiply the variables plus the functions. Okay? And simply all of this we can write as the x with xm, the x prime, the matrix x equal the matrix A multiplied with matrix x plus the f, okay, the matrix f, or the function.
Okay. Then this is if the system homogeneous, or the f is equal to 0.
So basically, remember that in the differential equation that we did in engineering math 1, what we want to know is the solution, right? So you have like a differentials. Suppose that maybe y prime or dy dt or y prime equal something y plus another function of x or t. Then we want to make, or we want to find what is the possible y, or what is the possible for the whole function that can be satisfied with this x prime. Or in this case, what we want to find is this x. Okay? We want to find this x, the solution for x.
We call that x as a solution factor. Okay. So I think as long as you now understand all the differential equation can be written as in this matrix, I think that's okay. And this is what we want to find.
And this will satisfy the system that we previously observed. Okay? And similarly, we also have the initial value problem, which is, I think, pretty useful, pretty regular in differential equations, especially in engineering math 1, right? So we want to find if we have a boundary, which is usually we have the initial conditions that we can set up to find the particular solution or the unique solutions. So we are going to set this, the x, at the variable t naught or t, and we say that we have the initial condition. This is the initial conditions. Right?
So we are going to set this
As a solving this differential equations subject to this constraint or the initial conditions. Okay, and I think that is
supposed to be okay, no problem at all. So it's pretty much the same with what you have before, what we have learned before in engineering mathematics 1. The difference is we need to rephrase all the terms in terms of matrix. Okay. And then this is also the same. It's pretty much the same, but the difference is this is going to be the matrix. Okay. So we are going to have the
matrix A, matrix F. It's a continuous functions in the interval, common interval, same interval contains the point, the parameter that we want to constrain. This is the initial condition. Then it should exist a unique solution. Like for example, if you have the first order, or maybe you have at least for the first order, you need to have one initial condition, right? If you have more, then you need to have like a more initial conditions. So you have the unique solution. If not, then maybe you will have like some possible solutions that we don't really know which one is the one we are looking for. And there will be the interval that we are going to observe, right? And I think that is when we learn about the the phase, right? The phase. When you did the autonomous first order, right? That's we learned how to imagine what would be the trajectory, right? And another theorem is the superpositions, which I think this is also the same what we have in the engineering math 1. So I think if you check your notes, it's supposed to be the same. The difference is we are going to define this in matrix. Okay? So let's look at this matrix now. We have matrix x1, x2, and until xk. It's a solution vectors that are in satisfying the homogeneous system on some interval. And if we have the linear combination with some constant C1, C2, Ck, that also a solution. That's also a solution. So linear combination is also a solution.
And from this superposition, we can also set another theorem, another theorem which set the linear independent solution. This is also still very similar to what the differential equations, the regular differential equations. So we could say that
if we have these combinations linearly, and if we could make that combinations equal 0, then that will be the linear. We can expect it can be dependent or independent if we know the combinations. So if this is equals 0 for every parameter t in the interval, if the set of vectors is not linearly independent of the interval, it is going to be the linearly independent. And the idea of this independent or dependent can be solved immediately through our Wronskian. Let me zoom out.
And I hope you still remember the Wronskian. Basically, it is set of
solution factors. Okay, it is going to be linear independent if the Wronskian is not 0, and this is going to be our set of all the x, and basically we want to make it the first derivative, second derivative, right? And then we take the determinant and do some Cramer's rule, right? If you remember. And whenever it's not 0, then we are going to have the independent, linearly independent. And then after we get the linear, so we want linear independent. Okay, if that is linear dependent, that is not going to be unique solutions. Okay? So we want to make sure that every solution that we have is linear independent. Okay, and the solutions that we are going to have, we are expecting some fundamental set of solutions. Okay? We are going to see the solutions. It could be for non-homogeneous, we need to include the homogeneous one. Okay. Now we are going to walk through from the homogeneous system. So if we get the linear independent, we get the fundamental set of solutions. And the fundamental set of solutions is going to be exist on the homogeneous system, and then we can see the general system in the general solutions of the system. We could have this combination of constant and variables as well. I think this is pretty much similar. We just change the variables with the matrix. We just change the variable with the matrix. So we have the homogeneous
and we have the non-homogeneous. And remember when we did the differential equations, every time we did the non-homogeneous, we need to start taking the homogeneous, and
usually we take constant coefficient equal to 0 and then find the the characteristic equations, right? So we have another one here, and this is, usually we say the XP as a particular solution, if you remember, particular solution. So we have the solution for the homogeneous, and we have the particular solution. This is for the non-homogeneous, and we need to combine the homogeneous and non-homogeneous to get the whole general solution. Okay. So remember that we are going to have the XC and XP. It is one. Okay. So XC is for the homogeneous, XP is from the homogeneous. C is from the complementary function. Okay, I think that should be okay for just a overview. Okay, for overview. So first, I think the idea, we are going to expect that there is going to be initial value problem, which we have the differential equations, and we also have some set of constraints that we are going to check our solutions. And then we are expecting to have either homogeneous or non-homogeneous. We are expecting to find the solutions, which they are going to be, we could call the fundamental set of solutions, which the solution for homogeneous and non-homogeneous will be different. For non-homogeneous, we still consider the homogeneous part, which we call the complementary. So the whole expected solutions will be the XC plus XP. Okay, this is what we are expecting. And by doing that, we are going to have some set of methods and conditions that we might have in differential equations. So let's start for a while. Okay. Let me start from maybe giving you let's start from Okay, we start from this homogeneous linear system. So I will start this homogeneous by taking some verifications. Okay, so suppose that we are going to verify on the interval, for all interval here, that is if we have the x1 and we have x2, these two are solutions of x1 okay, now we are going to see, so this is not solving a problem, we just need to verify whether these two are solutions. So what we need to find is we are going to multiply. Remember that this is the original equations, so this is going to be the A, right, the matrix A, the coefficient. So the AX1 1 3 5 3, we are going to multiply with that. I will multiply and then this will be E with negative 2t, and this will be E or negative 2t. So we just multiply as usual, and this will be 1 minus 3, right? 1 minus 3 is minus 2. And 5 minus 3, this would be 2. So this is equal to x1
prime. So if we multiply this with our solution, this will be the x1 prime. And also the same thing, we take ax2 oh wait, wrong. This is 3e60 5e60. This will be 3 plus 15 18e60. 15 is 30e60, and this will be equal to x2 prime. Now if we check through the Wronskian, we write here, checking independency through the Wronskian. So we can write W x1 x2. So the x1 is e negative 2t, negative e negative 2t. This is 18 or 3e 60, 5e 60. And take the determinant, and we get that this will be 5e 4t minus or plus, right? Minus 3e 4t. So this will be 8e with 4t as power, and this is not equal 0, which means that this is going to be linear independent. So x1 and x2 are linear independent. So the general solutions, from this example, we can write x equal c1 x1 plus c2 x2, and we still just write c as long as we don't really know the subject, right? If we are not having any constraint, then we just write this c. So this will be x c1 1 negative 1 e negative 2t plus c2, this is 3 5 e 60. Okay. Okay, let me copy this. Let me just copy this page. So let me copy. Same. Okay, before I will erase a little bit. And we are going to see how we can now include the eigenvalues and eigenvectors. Okay, I will erase this part. Okay, erase this one. Okay, we have this, and we are going to use this as our example. Okay, we see that from these two solutions, both solutions have the form xi, k1, k2. This is going to be E lambda I t, which I can be 1, 2, where k1, k2, lambda 1, lambda 1, lambda 2 are constants. So we can always find a solution of the form x k1 k2 until kn multiply with e with power of lambda t equal, we can say the k vectors as just single k e lambda t. Now this is now become our general linear system. Okay. So solution of the form, we write completely, of the form for general homogeneous linear first ODE x prime a x. So this will be the solution. So solutions, so let me write here maybe, so solution is x equal k e lambda t. So this is solution for this one. And this is supposed to be with A is n by n matrix. We need to have an equal size row and column. If not, then we cannot find the determinants, right? Okay. Okay, let me copy again. And let me erase this. Okay, so we can write here the x prime or maybe this is maybe let me write with the new line, maybe let me write here, let me write from here. Okay, and okay, so if the solution is this, then if we take the derivative of the x and then take derivative, so k is still k, and e will be lambda e lambda t, right? And then we can also substitute that into this equation. So we are going to substitute this to that and this to here. So we have k lambda e lambda t equal a k e lambda t. We are going to get a k lambda k, the very original, the eigenvalues that we discussed earlier. So we can say that a k minus lambda k equals 0. Since k equal the identity k, then we can write the same equations as we did, a minus lambda I multiply with k need to be equal to 0. Okay. So we can write the equations for all k, and when it's minus lambda identity, which means this is going to be the diagonal part. Okay. So we are going to write the system. So system of linear algebraic equations becomes a11 minus lambda k1 plus a12 k2 plus dot dot dot. This is a21 k1 plus a22 minus lambda k2 plus dot dot dot. This is, let's say, a1n kn plus a2n kn equals 0. This is going to be lambda, or a mn minus lambda kn. So to solve this, so we need to find non-trivial solution. K that satisfy this a lambda a minus lambda Now to get k, again we are going to settle the determinant to get the eigenvalues. Okay. So because we want the non-trivial k for the solutions, then from the conclusion from the equation here, then
the determinant should be 0, which this is going to be
how we find the eigenvalues. And again, this will be expecting the characteristic equation to find the eigenvalues. And then we expect to get the solution x, k, e, lambda t. Okay, so this is, we want this. Okay. Maybe just one more for the types of the equations, the next part. That will be the, I think, our last discussion for today's class. Or maybe just end up to here, okay? Just up until here. Then next, because it have some examples that I can show. Maybe I will give the examples next week, okay? So I think up until here, any questions so far?
I think this is just introductory to shift from the differential equation in engineering math 1. Replace all the terms with matrix. Hopefully you still remember some methods from engineering math 1, or no? Okay, at least the characteristic equations still remember. Like we usually write with m, right? M squared, and that is for the degree, right? For the order. And then we set the equal 0, and then we find the roots, right? We have the distinct roots, we have the multiplicity, and we have the complex thing that's similar, right? Okay, anyway,
we're going to see each other next Monday for quiz. I hope you're ready. I prepare the questions. I think 2 or 3, I forgot, 2 or 3. So as long as you can compute matrix, find the inverse, row operations, and basically there's pure raw math. And as long as you are avoiding mistakes, compute correctly, you're supposed to be okay. You can take calculators. I'm not sure calculators can help. If the calculators can input matrix, maybe it can help confirm your solutions at least, but you need to show the details, okay, in your paper. But I mean, if you want to know whether this is correct or no, then if the calculators can compute matrix, maybe it can help. I think some calculator can input matrix, right? But not sure. Not sure your calculator can do that. You can check first, okay? Okay, if there's no questions, let me just disclose this and brings you up.